So I want to do one more thing before we leave off of this problem, and that is return to this idea that thermal resistances are your best friend in terms of understanding heat transfer problems. And sometimes you use them at the end to make sure that what you just calculated makes sense. Probably it would have been better if we would have used these at the beginning to figure out what we need to calculate and what we don't. But if I look at this hay bale, I cannot simulate what's going on inside of this hay bale exactly using thermal resistances, right? The thermal resistance equations that we derived were for steady state problems where there was no thermal energy generation. But what I can still do is use thermal resistances to understand what's important and what's not, and to make sure that what I'm calculating actually makes sense, right? So physically, if you think about what's going on in this problem, I have this big hunk of material, and inside the material, it's generating thermal energy, right? So there's a total amount of thermal energy that has to get out, and it has to get out through three resistances. It has to, first of all, be conducted through the bale, right? Not all of it has the same path. Some of it's generated towards the center and has to go a long way. Some of it's generated right here at the edge and doesn't have to go very far. But all of it has to go some distance, right? And that's a resistance. That resistance, it goes in my sort of approximate network right here. And then once it gets to this surface here, it has to be conducted through the plastic, and finally it has to be convected to the air. So each of these mechanisms has associated with it some thermal resistance. And if I want to make sure that what I'm calculating is sane, right, that it makes sense, I can calculate each of these resistances, and I can calculate the total amount of energy that I have to push through them, and I can see whether the temperature rise that I get when I push this energy through these resistances, is it all consistent with the temperature rise that I just calculated and plotted here in ease, right? Ease, when I did this fairly sophisticated analytical solution, this is the temperature rise I'm talking about, right? Right here, this is the temperature rise that happened because I had to push the energy through the bale material and then through the plastic and then out to the surroundings, right? Is this anywhere consistent with the temperature rise that I would calculate if I just kind of stepped back and said, how big are these resistances and how much energy do I have to put through them? So that's the idea, right? Some of these resistances I can calculate exactly. There's an exact resistance associated with the conduction through the plastic. We've already calculated that. There's an exact resistance associated with convection. Already calculated that. I can calculate exactly how much energy is inside of this hay, right? It's just the volume of the hay multiplied by the rate of volumetric energy generation. So I can calculate this guy. This guy here, I can't calculate that exactly. And again, the reason is because not all of the energy experiences the same distance that it has to be conducted, right? Some of it has to go a long way. Some of it only has to go a very short way, but I can estimate it pretty well, right? And the way you estimate resistances, if you can't calculate them exactly, is with this equation that we'll come back to over and over again. I have to estimate how far does the energy have to move, divided by the conductivity, and then about what is the area for conduction, right? And you can argue with me to within factors of 2 of each of these guys, right? But you have to remember, I'm not trying to get an exact answer. I'm just trying to get a feel, a ballpark estimate. So how far do I have to move energy? Well, the farthest I'd ever have to move it is the radius of the bale, right? You might say that on average, maybe it should be more like R bale over 2. So I'll use R bale over 2. And then what's the area for conduction? Well, it changes from 0 to this area out here at the outer radius. I'm just going to use the area out here at the outer radius, right? And this I'll use to estimate the resistance of our conduction bale. So that's what I did here, right? I estimated our conduction bale. This is me calculating the total amount of energy generation inside of the bale. And then I can use that to figure out what is an estimate of the temperature at the center of the bale. The temperature at the center of the bale is T infinity plus G dot multiplied by those 3 resistances are in series, so we'll add them all together. And what I find is this approximate temperature is within a few degrees of the temperature that we calculated exactly, right? And that gives me some comfort that I didn't do something wrong, right? As long as this approximate temperature is within 50% of what we calculated, I think it makes a lot of sense, and it's within the realm of reason. If I would find that this approximate temperature is 100 times bigger or 100 times smaller, then I probably made a mistake somewhere in my analytical solution. The other thing that's interesting is I can actually look at these resistances, right? So here's the resistance of the bale, here's the resistance of the plastic, and here's the resistance of convection. So if I throw those resistances onto this network, it tells me something that would have been actually kind of useful to know way at the beginning of this process. And it tells me that, if I look at the magnitude of these resistances, the only one that matters is the bale. The plastic is not a resistance that matters at all in this problem, and neither is convection, right? These guys are so much smaller than our conduction of the bale that I didn't really need to even model these. In fact, the resistance between this surface right here and the surroundings, that resistance is so small that this T infinity is basically going to be equal to the surface temperature at the outer edge of the bale, right? I mean, that's what this is telling me, is this temperature right here is going to be really close to 70 degrees Fahrenheit. All of the temperature drop occurs inside of the bale. Almost none of it occurs from the surface of the bale to the surroundings. And if I go back and look at my temperature distribution, right, so that's what this is. Yeah, this outer edge right here is 68 degrees, 20 degrees Celsius. I've basically pinned this outer edge to the air temperature. So kind of what that says is I could have made my analytical solution a lot easier by just having a boundary condition that was T at R equals R bale equals T infinity for this problem. Right? That's just how it worked out. This thing that I just calculated or estimated, right? This ratio of the resistance inside of my body to the resistance from the surface of the body to the surroundings is called a BO number, right? We'll come back to that a lot of times. And when that BO number is really small, I can ignore temperature gradients inside of my surroundings. In this case, the BO number is really, really big, right? And I can't ignore temperature gradients inside of my body because they're everything. The temperature gradients from the surface to the surroundings are very small. The temperature gradient inside of my body is basically the entire temperature gradient, right? So this is sort of the opposite of what we will call a lumped capacitance problem, or this is the opposite of what we would allow an extended surface approximation to be, right, when we get to those things. All right, one more thing, and then we'll be done. And that is a question, I guess, which is, we ignored radiation from the surface of this bale. We said that radiation, we're not going to consider it in our model. It might be a nice idea to come back and decide whether or not that was a justifiable approximation or whether we maybe ignored something that was actually important. So if I wanted to think about whether or not that was a good idea, what I need to do is recognize that, when I get to this approximate resistance network, radiation forms a parallel path here to convection, right? So I basically have now this resistance network here. And I guess I would ask the question, when would radiation be important and when wouldn't it be important? So it's actually kind of interesting because if you think about it, radiation will never be important for this problem. It's impossible for it to be important. So let's think about that for a second. If I calculate a radiation resistance and it's really, really large relative to the convection resistance here. So the convection resistance is 0.01. Let's say I calculate a radiation resistance and it's 1 Kelvin per watt, right? That's really large. It's 100 times bigger than 0.01. Well, what's going to happen? All the energy that comes through this network is going to want to go through the convection resistance. None of it's going to go through the radiation resistance. This resistor is not important at all, right? Large resistances in a parallel combination are not important. It's always the small one that's important. So if radiation resistance is really large, it's not going to matter. The parallel combination of 0.01 and 1 is really, really close to 0.01. What happens if the radiation resistance is small then? So let's say I calculate this radiation resistance and I find that it's 0.001, right? So it's 10 times smaller than our convection. Well, now when I look at these two guys, I would decide, radiation resistance is really small relative to convection. Convection isn't important anymore, right? So I'm going to come in here and I can cross this guy out, because this guy is 0.001, right? This is the direction that all the energy is going to take. But if you look upstream of these resistances, the parallel combination of these two guys now is going to be really close to 0.001, right? So this unimportant resistance just became even more unimportant, right? This is now an even smaller resistance, which when I compare it to the bale is even less important. So I can still cross out all of this stuff and all of this stuff and say, for this particular problem, conduction in the bale is the only important thing, right? Radiation can never be important. If it's big, it's not important. If it's small, it's not important, right? That's not obviously a general conclusion. That's a conclusion for this particular problem, just given the way the other resistances in the network sort of stack up, right? And again, I hope you see that the point of this is thermal resistances are your tool for understanding what's important and what's not. I have a really good handle on what's important in this hay bale problem now, based on the fact that I estimated these thermal resistances, right? I can really start to predict whether, I don't know, if the wind blows, is it going to matter? Is my hay bale going to be significantly cool? Well, no, it doesn't matter, right? This convection resistance isn't important. If I double the thickness of my plastic, is that going to cause a problem? No. This is a small resistance. I can make it twice as big. It's still not going to be important, right? Now, if I start making bigger hay bales, that's a problem, right? That's a problem because this resistance that's important goes up and this generation goes up as well, right? So I have a very physical understanding for my heat transfer problem at this point. Okay, so that's thermal energy generation. We're going to use 1D problems with thermal energy generation as the jumping off point to start talking about numerical solutions in our next lecture, right? So we solved this one analytically, right? We had a function that solved a differential equation. That's an analytical solution. What we'll talk about next time is sort of your ticket to avoid that kind of differential equation. So if you don't like differential equations, you're going to love numerical solutions because you end up solving algebraic equations.